while discussing the table of step 5. In
Excuse
this
me, sir.
table, we have find out the value of efflux by a hit and trial method for different river stages, for different river states, and for different discharge levels. We are given a single value of discharge, but during the design life of barrage, it's not necessary that discharge equal to this will be occurring. In fact, most of the time discharge less than this, or there might be a chance of discharge greater than this. Design maximum design discharge might occur. Considering that various discharges were considered and various river stages were considered for which the value of efflux was found using a hit and trial method. In last class, this was done for main weir portion. The same practice has to be done for the under sluice portion. But the difference that for main weir portion, we have considered various discharges. For under sluice portion, a, a single value of discharge or discharge with 20% concentration is considered. The discharge calculated at the end of step 4, the discharge passing through under sluice is multiplied here by 1.2. The column 1 downstream water levels are corresponding to 20% concentration discharge water levels seen from rating curve for 600,000, 601.5, 595, and 604. These are the downstream water levels for 20% concentration. A value of efflux is assumed. Rest of the things are more or less the same as was for the previous step, with the difference that here the discharge is only for weir. Here the crest level for determining the weir submergence is crest level of the undersluice portion. Here the width of the weir is the width of undersluice portion only, not rest of the weir. You have to balance column 1 and column 17, or you have to assume a value of a flux such that column 1 is near to column 17 or 17 is near to column 1. If not, revise the value of a flux and C dash over C seen from the Gibson curve given on your book, given in your book and on your slides. Next step is setting or adjusting the downstream flow level. For adjusting the downstream flow level, I'll be using three different methods. First, named as Blanch method, second named as Crumbs method, and third, a conjugate depth method. In all of the three methods, we'll be adjusting the downstream flow levels, or the purpose of using the three different methods is to apply a check. We'll set a downstream flow level by Blanch method, and we'll check either the provided downstream flow level is okay or not by the rest of the two methods named as Crumbs and conjugate depth methods. The downstream flow level is depending upon the formation of hydraulic jump. Water, after passing over the weir crust, upstream of the weir crust, it is in subcritical state. A hump has reduced the area of flow, which increases the velocity of flow to the critical velocity. Downstream of the crust, the flow state becomes supercritical. We need to change that state of flow from supercritical to subcritical one. And one of the methods of doing this is to provide a pool whose depth is either equal to or greater than the conjugate depth. Conjugate or sequent depth denoted by D2. For any flow, if D1 is the depth before the hydraulic jump, it will be having a depth D2 known as its sequent depth, which can be calculated by the formulas expressions of hydraulic jump studied in hydraulic engineering course. In this part, we won't be using the expression. Instead, will be using you will be using two or three different methods which are developed, which are prepared using the same equations of hydraulic jump, or the equations of head loss and equations of sequent depths. Right now on slide, uh, these are known as Blanch curves. On my right are these curves in SI units. On my left are these curves in FPS units. X-axis of these curves is head losses, head loss in through a hydraulic jump. and y-axis is specific energy at the end of hydraulic jump. E12 is noting specific energy at the end of hydraulic jump. If we know the specific energy at the downstream side of hydraulic jump and the downstream energy level, the downstream flow level can be difference of downstream energy level and the specific energy at the end of hydraulic jump. Initially, this incomplete table is shown, and then the same table is filled with the values as in book. The first column of this table is same as second last column of the previous table. Previous two tables. This column 16 for main weir and column 16 for undersluice quotient. First for main weir, then for undersluice quotient. Upstream energy level is the sum of upstream water level and velocity head, seen again from the table in step 5. Upstream water level plus velocity head is upstream energy level. Downstream energy level is downstream water level plus velocity head for this table. Upstream and downstream energy level, they can be determined from the table in step 5. So head losses will become difference of upstream and downstream energy levels. From the value of specific discharge and head losses, you have to consult the Blanch curves. For any value of head loss, say 10 feet, and a specific discharge of 10 cusics per feet, specific energy on the downstream side is 4 feet. So for your case, you have to see, you have to calculate head losses and specific discharge passing over the weir. The downstream flow level will become, or downstream flow level will be lower than the downstream energy level by E2. If this is the energy line known as downstream energy line, and specific energy downstream on the downstream side of the hydraulic jump is known, the downstream flow level will become downstream energy level minus specific energy here. This is our downstream flow level. Now you see we are obtaining various values of downstream energy levels. Downstream water levels. They are various values of downstream water levels for main weir and various values of downstream flow levels for the undersluice portion. Of these values, we have to select the lowest value. Reason being, if we select the lowest value on the downstream side, the lowest flow is provided depth either equal to D2 or sequence depth for this case will be present, or depth greater than D2 for rest of the cases will be present for these discharges. Similarly, for the undersluice portion, we have to select the lowest value of downstream flow level. Please, is this method clear? Please go through this table right now. See this table right now. If you feel any questions, any difficulty, how it's done, please ask. The second method is adjusting the downstream flow level and flow length by a Crumbs approach. The next step, adjusting the downstream flow level. The same thing which I have done in previous step. The flow length was left in the previous step. So in this step, we'll use the same downstream flow level as decided in previous step and apply a check to that either the provided downstream flow level is correct or not. And further, we'll decide the length of downstream flow. For this, again, that can be done for all of the various conditions as done in step 5, as done in this table of step 5 for main weir and the undersluice quotient. The solved example in the book is doing this only for design discharge and maximum and minimum values of downstream water levels. So initially it's done for the maximum value of downstream water level. The maximum value of downstream water level is for design discharge of 500,000 cusics. Please consult this table again. For discharge of 500,000 cusics, I am having three downstream water levels: 600, 596, and three values. The maximum is 602.5. And corresponding to this 602.5, the upstream water level is 604. The velocity head is 0.89, so upstream energy level becomes 604.89. These values are used here. The riverbed level is same for all the students and me. Crest level, that this might be slightly different for you. Depth of pool. As in last step, we have adjusted the floor level to a lower elevation, and we will be terming that as a pool. The depth of that pool will be the difference of the downstream water level and downstream flow level. This downstream flow level as decided in the previous step in the Blanch method, जो भी मैंने from which we started our today's class. So velocity on the downstream side will become Q over A, where Q is discharge, design discharge, over area of flow is width between the abutments and depth of the pool. Velocity at V square over 2G. So, so the downstream energy level will be downstream water level plus velocity at this is our downstream energy level. And head losses is difference between upstream and downstream energy levels. The difference here from the last is previously we were considering the velocity at same on upstream and downstream side. But actually now we are refining that assumption by on these curves. From this curve we'll be using the line this K plus F over C line and the horizontal axis of L over C, where L is denoting head losses and C is denoting critical depth. Now I'll calculate on my calculations. I'll calculate. We have calculated a value of head losses and C is critical depth. Critical depth from this ratio of head loss over critical depth, a value of K plus F over C can be seen from these curves. For this K plus F and this K plus F over C is K is the specific energy over the Weir crest, F is elevation of hydraulic jump from the Weir crest, and C is critical depth. Where energy head over the or specific energy over the Weir crest can be difference of upstream energy level minus crest level, the same crest level as decided in the step 4 and for step 3 and step 4. Critical depth is cubic root of Q square over G, where Q is specific discharge. L over C, L is head losses, C is critical depth. For this value of L over C, we have to see a value of K plus F over C from Crumbs curve. For our L over C value of 0.2, it will be somewhere around here. K plus F over C is slightly lesser than 2. It's around 1.94. Rearranging this in this K plus F over C, we know the value of K, which is energy head over the Weir crest. C is critical depth. Only left unknown is C. Rearranging this equation to determine the value of F. F is calculated here, where F was the position, the elevation of hydraulic jump with respect to the crest level. A reduced level of hydraulic jump can be the position is termed here as position of hydraulic jump can be determined by subtracting F from the crest level. Crest level, the hydraulic jump is 2.6 feet below the crest level. The position of hydraulic jump is 586.39 for my case. E2 here is denoting specific energy at the beginning of hydraulic jump. Here you have to be careful. I am using the same notation as in book. Don't get confused as in In Blanch method, E2 was denoting specific energy on the downstream side of hydraulic jump. Here it's denoting specific energy on the upstream side of hydraulic jump. So the specific energy will be downstream difference of downstream energy level, which is given to us and position of hydraulic jump, specific energy at this location. Position of hydraulic jump, downstream energy level. Subtract position of hydraulic jump from downstream energy level will give us the specific energy at the position of hydraulic jump. Submergence of hydraulic jump or the height of hydraulic jump, the height of position of hydraulic jump with respect to downstream flow level is termed as submergence. It should be a positive value. It's a check on our provided downstream flow level. If it's a positive value, it's okay. If it is coming out to be negative, we have to revise our downstream flow level. We have, say for example, this value was minus 2 feet. So then we will change our downstream flow level to 574. Remember, at this step, no need for going again back to the previous step. If there is some change in downstream flow level, make a change here and move forward. No need for going back. Downstream flow length. The downstream flow length of the concrete floor should be equal to length of hydraulic jump. For this case, hydraulic jump is occurring slightly upstream of the toe of the glacis, and that can be easily calculated, known the submergence of hydraulic jump as 10.39 and slope of downstream glacis as 1:3. So the horizontal distance upstream of the toe of the glacis will become 10.39 into 3. If hydraulic jump will start here, it will be extending a length equal to 4.5 times E2. If it is some distance upstream of the toe of the glacis, downstream of the toe of the glacis, the length of concrete flow required can be calculated as 4.5 times E2 minus 10.39 into 3. This will give us the flow length required downstream of the glacis. Here now it's done only for one of the cases, only for one of the discharge, for one of the discharge or for and for the and maximum water level for that discharge. Repeat the same procedure for minimum water level and check either the our hydraulic jump is submerged or not, and what is the length of flow required. The same procedure is repeated, and at the end you see this step is giving length of concrete floor as 74.41 feet, whereas previously it was 43.48 feet. So we'll select the larger value. Another interesting thing to be noted here is it's not necessary always the higher values are more critical. Higher value is giving less flow length, whereas a lower value of discharge, a lower value of downstream water level is giving us greater value of downstream flow level for the same discharge. So that's the reason why we make checks for all the scenarios, so for different scenarios. Book is solved example is of the book is solving this only for the maximum discharge or the design discharge and minimum and maximum water level. This can be done for other discharges as well, other lower discharges as well. For your case, for your assignment part, you can solve, you can do again for the design discharge, minimum and maximum water levels. The same procedure is adopted or followed for adjusting the downstream flow length and flow level by the Crumbs approach. The design discharge for undersluice is proceeded with 20% concentration, or the design discharge calculated at the end of step 4 is multiplied here by 1.2. The downstream water level corresponding to this discharge, upstream water level corresponding to this discharge, upstream energy level corresponding to this discharge are seen from this table. Determine the water levels for the undersluice portion. The maximum value of water level, downstream, upstream water level, and the Velocity head added to upstream water level gives us the value of upstream energy level for the undersluice portion. Riverbed level is same for the undersluice portion. Crest level is lower lower as compared to the main weir. Depth of pool same as in previous step. Velocity here will be different. Reason being here we will be using width of the undersluice portion only. Velocity head calculated. Downstream energy level will be downstream water level plus velocity head losses difference between the upstream and downstream energy level. K same as done in the previous step. C same as done in the previous step. The critical depth of flow. L over C. K plus F over C seen from the Crumbs curve. F value calculated by rearranging this and the position of hydraulic jump is 3.37 feet lower than the crest level for the undersluice portion. Similarly, E2 specific energy at the beginning of hydraulic jump submerges difference of downstream flow level and the position of hydraulic jump. This downstream flow level as decided in the first method. The downstream flow length will be the difference or the position of 4.5 times E2 minus position of the hydraulic jump in horizontal direction. Again, the same steps are repeated for a minimum value of discharge, and again the minimum value of downstream water level, and again the lower water level is giving us greater value of the downstream flow length, which will be provided for the undersluice portion. Any questions from this part, the second part? Up to now in today's class, I have shown you two methods for setting and the downstream flow level. And then in the second method, we have seen a step to decide the length of downstream concrete floor. Third method is a check applied on the length of the level of provided downstream floor level. As the step says, checking adequacy of downstream flow level using a method known as conjugate depth method. For this method, I'll be using the tables provided in your book. On page 73 of your book, there are tables conjugate depths. Conjugate depths can be for calculating conjugate depths. D denoted by D1 and D2. We see two factors denoted by Z and Z dash from these tables for various values of Fz, where Fz is calculated as Q over E raised to power 3 over 2. Here Q is specific discharge and E raised to power 3 over 2. E is the difference of the upstream energy level and downstream flow level. Select a value of discharge in the first step. Say 80% is passing through mean weir. Upstream energy level, first solve it for maximum value of upstream energy level, then adopt this method for minimum value of upstream water level, upstream energy level. Corresponding to this upstream energy level, what's the downstream water level, downstream flow level, E value calculated by difference of upstream energy level and downstream flow level. Q is specific discharge, Q over width. Fz is small q discharge over E. Z seen from the tables, and D1 is product of Z into E. Similarly, Z dash for C, this Z dash for phi is equal to 1. Z and Z dash seen for Fz value. D2 calculated by Z dash into E. Depth of pool created on the downstream side as done in the previous step, the difference of downstream water level and downstream flow level. Jump submergence. It is if the depth of pool is greater than D2, it will be a positive value. value. It should be a positive value. If it's a negative value, if positive, if negative, revise, reduce the downstream flow level. If say this value comes out to be minus 3 feet, reduce the downstream flow level by 3 feet. You will be doing this for different conditions, different scenarios. And if in any scenario the value comes out to be negative, just reduce the downstream flow level by that value and move forward. No need to go again back to the previous steps. I'll explain these simple calculations. Up to this step, for the main weir, our downstream flow level is set as 576 feet. For the undersluice portion, the downstream flow level is set as 573 feet. In the Blanch method, from where we started our class. In next step, applying Crumbs method, we have seen these provided flow levels are working okay for two different scenarios. And then further, we are seeing this for four different scenarios, applying another method. If discharge is 500,000 cubic, consider 80% is passing through undersluices. For this 500,000 cubics, maximum downstream water level is 602.5. Maximum corresponding to this, upstream water level is 604. Upstream energy level is 604.89. Seen from the table in step 5. E is denoting the difference of upstream energy level and downstream flow level, as shown on the sketch of this conjugate depth method. Q is specific discharge, discharge over width of flow, where width of flow is width of weir minus width of undersluice. Depth of pool is the depth of water on the downstream side of the weir, which is calculated by difference of downstream water levels and downstream flow levels. E raised power 3 over 2. This E to 28.89 raised power 3 over 2. Fz is Q over E raised power 3 over 2. For these values of Fz, we consult conjugate depth coefficients from tables and see Z and Z dash values for 1.073. For 1.073, 1.04, 1.1. Interpolate a value in between 1.04 and 1.1 to obtain a value of for 1.07 in between 0.14 and 0.15. Z and Z dash are seen from this table I have shown you. See a value of Z dash for phi is equal to 1. So jump submerges is depth of pool minus D2 calculated here. If it's a positive value, that means depth provided on the downstream side is greater than D2 or greater than sequent depth. A hydraulic jump can form on either on upstream side of the toe of the glacis. This is done for maximum minimum value of design discharge, for 50% of design discharge maximum minimum values, and then for undersluice portion. For the solved example in the book, the jump becomes submerged for all cases. And if for your case this values by any chance become any of these values become negative, just reduce the downstream flow level at this step and no need to revise the previous steps. Just change, say for example, this value was minus, if comes out to be minus 2.69. Reduce the downstream flow level by 3 feet and move to the next steps. No need for going back into the previous steps. This will be your assignment related to today's part of your class. You have to set the downstream flow level and length using Blanch, Crumbs, and Conjugate depth methods, with the three methods which I have discussed in the class today. You have to do these methods manually. Table in the step 5 for main weir and undersluice. This can be prepared on in an Excel worksheet. Rest of the steps are to be done manually. Please, any questions?